a total variation, I usually write as TV, is equal to integral over the entire domain. So if the domain is from 0 to L, I'm integrating between 0 and L. If the domain is between A and B, I'm integrating between A and B. The absolute value of du dx times dx. So total variation, of course, is a function of t, because I integrated over x, I did not do anything about t. U changes as a function of t, so the total variation also changes as a function of t. So what does that mean? Let's take a look at the total variation for, first of all, for monotonically increasing function. So can somebody tell me, if I have a monotonically increasing function, what does this total variation mean to you? Can you visualize it? Or can you compute it? Yes?
It's just u of L minus u of 0?
Yes, if du dx is positive, monotonically increasing, this is just the u of L minus u of 0. It's the highest point in the function on the right hand side minus the lowest point on the function on the left hand side. Right? Okay, so what if it's monotonically decreasing? It's going to be u of 0 minus u of L, right? So still the highest point of the function minus the lowest point in the function. Now the tricky part. What if the function is increasing from 0 to some point in the middle of the domain, then decreasing from there on? You can break the domain into these two parts. On the first part, the integral is equal to the highest value of the function minus u at 0. On the second part is still equal to the highest value of the function minus u at L. Right, so if I have, in general, if I have a function that is increasing, decreasing, increasing, decreasing, increasing, decreasing, okay, what is the total variation? You can use the same logic. Break the function apart into monotonic regions. It is basically this value, the absolute value of this range, plus the absolute value of this, plus the absolute value of this, plus the absolute value of this, and plus the absolute value of this, and then this. So that's why it is called total variation. The total amount of variation of that function. And I claim in a scalar conservation law, the total variation is not conserved. It does not increase. It can only decrease. Okay? And to see this, we can look at the same function and think of, for example, for Burger's equation, how would this initial condition evolve? And for any conservation law, how would this function evolve? So here we don't have any discontinuity, right? So the function would just evolve according to the local wave speed. So for example, for Burger's equation, positive side would evolve towards the right. So negative, so let's say this is 0. Negative side is going to evolve towards the left. Positive side is going to evolve towards the right. And get negative side, positive side. The function would evolve like that. But I'm never going to create any new extremas, right? So after some time, the function is going to be like that. But no new extrema is going to be created. The monotonically increasing region of the function, if you bound it between the local maximum and local minimum, it's just the location of this maximum and minimum is moved. In between, if it's originally monotonically increasing, it's still monotonically increasing. If it's originally monotonically decreasing, it's still monotonically decreasing over the same range. So the total variation is the same if the solution stays continuous. So TV stays constant if U is smooth. Okay, what if U is not smooth? Now we can see a shock wave, let's say, is forming over here. What happens after a while? What happens when the local maximum and minimum starts running into the shock wave? what if this point keeps running towards the right, this point keeps running towards the left, and they run into the shock wave? Yes, the maximum starts to decrease. So when I get to this point, I'll have the maximum only over here because this maximum point has already disappeared into the shock wave. The shock wave is like a black hole. It just absorbs things. And when the minimum runs into the shock wave, the original minimum disappears and is replaced by a less negative minimum. And I also have things like this, right? So the maximum decrease, the minimum increase, the total variation is diminished. If U is discontinuous. So in both cases, no matter if U is smooth or not smooth, the total variation is going to be non-increasing over time.